Recently, the James Webb Space Telescope has unearthed a mysterious ancient galaxy, and it might completely change our understanding of the nature of dark matter and the process of galaxy formation. The telescope has managed to spot a stellar population bigger than our home Milky Way galaxy from 11 billion years ago, and it shouldn't actually exist. This galaxy is massive and is home to extremely old stars. They formed in the early universe. The problem is that this new observation upends our current cosmological models, since, by the time of the galaxy's birth, not enough dark matter had built up to seed such a formation. Researchers have been chasing this particular galaxy for 7 years. They spent endless hours observing it with the help of the two largest telescopes on our planet to figure out how old it was. Unfortunately, it was too faint and too red, so no one could measure it. Only after scientists moved their observations to space and started using the James Webb Telescope did they manage to confirm the nature of the galaxy. The thing is, unlike the Hubble Space Telescope, which orbits around Earth, James Webb moves around the Sun 1 million miles away from Earth. That's why it made it possible to see the galaxy clearer. Previously, astronomers were sure that in early cosmic times, there were very few huge galaxies. But recent findings challenge these theoretical models. Extremely massive dormant galaxies have been discovered as early as 1 to 2 billion years after the Big Bang and the beginning of the universe. The scientist who led the spectral analysis of the James Webb Telescope data said that they were doing everything possible to confirm the oldest galaxies that existed deep in the universe. When they did, it pushed the boundaries of the current understanding of how galaxies form and evolve. And now, the main question is how they managed to form so fast in the early universe, and what enigmatic mechanisms made them stop forming stars all of a sudden while the rest of the universe was still doing so. Galaxy formation is largely dictated by the concentration of dark matter. You see, around 84% of matter in the universe doesn't emit or absorb light. Astronomers call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. It supposedly affects visible matter, radiation, and the very structure of the universe. Finding extremely massive galaxies so early in the universe is posing serious challenges to our standard model of cosmology. All because astronomers don't think that such monstrous dark matter structures as the ones hosting those massive galaxies had enough time to form. Researchers need more time to figure out how common such ancient galaxies are and how massive they can be. But if they manage to find more of those, it will really upset our ideas of galaxy formation. But it could improve our understanding of the physics of dark matter. Bizarre ancient galaxies aren't the only thing discovered thanks to James Webb. For example, scientists have long suspected that supermassive black holes could have existed in the early universe, and this theory has been proven only thanks to the JWST and its infrared eye. It showed that an ancient black hole within galaxy Sears 1019 was actively munching on all the matter it could lay its hands on. This hole is from the times when our universe was less than 600 million years old. And that's another mystery we're yet to crack. It's supposed to take way longer than 600 million years for a supermassive black hole to grow to its full potential. Astronomers were watching the galaxy hosting the unusually old black hole as part of the Cosmic Evolution Early Release Science Survey. They saw the galaxy as it was when our 13.8 billion-year-old universe was just 570 million years old. Besides the ancient black hole, scientists spotted two other ones. Those probably appeared 1 and 1.1 billion years after the Big Bang. They also discovered 11 ancient galaxies that existed between 470 and 675 million years after the beginning of cosmic history.
Recently, scientists have discovered a humbling collection of monster galaxy superclusters, 662 in total. One of them is so ginormous it can make anyone terrified. It's called the Einosto supercluster, and it's located 3 billion light-years away from Earth. This particular supercluster was called after an Estonian astrophysicist who was one of the discoverers of the large-scale structure of the universe. This supercluster is truly staggering in terms of size and mass. Its mass is the same as that of around 26 quadrillion suns, which is 26 followed by 15 zeros. The galaxy supercluster is so huge that it would take a light signal 360 million years to travel from one side of it to the other. The rest of the discovered superclusters can't measure up to the Aenestos supercluster, and still, they are no slouches in the size or mass department. Using the discovered sample, a team of researchers led by astronomers from Tartu Observatory managed to calculate the average supercluster size and mass. It turned out that the typical mass of a supercluster in that collection was about 6 quadrillion solar masses, and the typical size of a supercluster was around 200 light-years across. It means that the average supercluster is more than 2,000 times larger than our home Milky Way galaxy. Another comparison for you. If the Sun had the same mass as a golf ball, a supercluster would be as massive as Mount Everest. During a closer examination of the properties of these superclusters, astronomers found out that galaxy clusters within these superclusters are heavier than those found outside the superclusters. It proves that galaxies in such superclusters grow and develop in a different way from galaxies elsewhere. But even though the superclusters have tremendous masses, individual galaxies they contain seem to be less dense than others. Most likely, it happens because this insane mass is spread across huge volumes. At the same time, supercluster galaxies are dense enough to have a tremendous gravitational effect on the matter filling the superclusters themselves, including their dark matter content. This matter is invisible to human eyes since it doesn't interact with light. Astronomers hope that the supercluster discovery will help us not only better understand how such vast collections of galaxies come together, but also allow us to figure out the answers to the mysteries of dark matter and dark energy. Our universe consists of normal matter, and dark energy. Normal matter, which is everything you can see with your own eyes or with the help of instruments, makes up around 5% of the universe. Dark energy takes up around 68%, and about 27% of the universe is dark matter. Now, dark energy is believed to be a force responsible for the expansion of the universe. Astronomers wouldn't even know the thing existed if, several decades ago, they hadn't found out that the expansion of the universe wasn't slowing down. Quite the opposite, it was accelerating. It meant there had to be some enigmatic force counteracting gravity. It was dubbed dark energy. As for dark matter, it is supposed to explain how objects work together. Potential candidates for dark matter vary from strange particles to super-dim objects. The European Space Agency's Planck satellite even helped astronomers calculate how much dark energy the universe has to contain to explain the way its expansion is constantly speeding up. But let's get back to our superclusters. The most curious thing is that the team behind the discovery has noticed that galaxies in these superclusters seem to be separating at lower expansion speeds than expected. What it means is still unclear, but hopefully, studying the superclusters will help us figure out the mystery of these troubling discrepancies observed in the universe's uneven rate of expansion.
In the heart of the galaxy, there lies Also, Sagittarius A star doesn't seem to have a very good appetite. It's been observed to be pretty quiet lately, which is good news for us. But even if it were super greedy, it wouldn't pose any threat to us. This black hole is over 26,000 light-years away. From Earth, we can see it in the Sagittarius constellation. In 2022, the Event Horizon Telescope collaboration released the first ever image of Sagittarius A star. It took years of collaboration and technology to capture this stunning image. And this is our second photo of a black hole in history. The first one was released in 2019, and it showed the supermassive black hole called M87 star. Yes, they both have star in their names. Don't try to make it make sense. Anyway, you may remember this photo as the first ever image of a black hole ever. It went crazy viral across the internet. And this black hole, M87 star, located in the Messier 87 galaxy, is way scarier than Sagittarius A star. You thought 4 million solar masses is impressive? Then how about 2.5 billion solar masses? M87 is a real monster. It's also known for its powerful jets of plasma, which are so energetic that they extend thousands of light years from the black hole's center. If M87 were a superhero, it would be Iron Man, with his repulsor beams on full blast. Now technically, you can't take a photo of a black hole itself, since it's, well, black. No light can escape its grasp. But the glowing orange ring in this photo shows the matter surrounding Sagittarius A star. It's called the accretion disk, a swirling disk of hot gas that spirals the center, heating up to millions of degrees in the process. It's like a giant fiery vortex, but with no escape. And the shadow in the center indicates the black hole itself. Inside that shadow, there's an event horizon. The event horizon is the boundary around the black hole, beyond which nothing, not even light, can escape its gravitational pull. It's the point of no return, where the gravitational force is so strong that even the fastest object in the universe, light, can't escape. Once you cross the event horizon, you're doomed to fall toward the center of the black hole, where the laws of physics as we know them break down. And this is exactly the fate that awaits our unfortunate X7. Right now, the pure blob is getting stretched and yanked by powerful tidal forces. By the way, before it meets its untimely demise, X7 is expected to put on a bit of a show. Its closest approach to the black hole, called periastron, is projected to happen in 2036. And when it finally gets torn apart by the Sagittarius A star's gravitational forces, there may be some cool fireworks to see. But this is not the most important thing. The funny part is, X7's future end may help us finally understand what the heck even is this thing. A team of scientists have been studying how a strange blob orbits the black hole. And that's when they discovered that X7 has stretched to almost twice its initial length. And what does that mean? Well, it suggests that X7 is most likely made of debris ejected during a recent collision between two stars. Yep, you heard that right, a space car crash. Imagine this. Two stars fall in love and start circling each other for many years. After that, they finally merge together. At this moment, they eject tons of gas and dust. And perhaps this cosmic dance created our blob baby, X7. It's basically like the crumbs left on the table after a giant space feast. Something like this is actually pretty common, especially around black holes. It's like a galactic fender bender that sends debris flying everywhere. Actually, the universe is full of mystery blobs. They're called the G objects. No, they're not the G-men from Men in Black, but they're just as mysterious and elusive. These guys have been puzzling astronomers for more than 20 years. They look like gas clouds, but behave like stars. It's like they can't decide whether they want to be a cloud or a star. Come on, guys, make up your mind. G objects stretch out at the closest point to the central black hole. but emerge intact, like a rubber band that stretches but doesn't break. Scientists think that they're the stars that have merged together into one. And while doing that, they also produce a huge cloud of gas that hides the result from view. Kinda like when you're wearing a bulky sweater, so that no one knows that you've put on a few extra pounds. And then a study published in 2021 found that one of these objects, G2, was actually a molecular cloud concealing 3 baby stars. Talk about a plot twist. But X7 is the black sheep of the strange blob family. It's significantly different from the G objects, like the weird cousin you see once a year at family gatherings. Its evolution has been more dramatic. Also, it's not being held together by a mass lurking in its center. So what is it being held together by? Pixie dust? Magic? We need answers! That's why scientists believe that X7 isn't a G object itself, but debris left from it. Or maybe not. We have no idea. The possibilities are endless, and that's what makes astronomy so exciting. So let's keep our eyes on the skies and see what other strange objects are out there. Who knows? Maybe we'll discover another mystery blob, and this time it's going to be a spaceship. Now that would be awesome.
The Milky Way is one of the biggest mysteries out there, literally. It's hard to figure out how big our home galaxy is, and one of the main reasons is because we live in it. Think of it as walking around a mall. You can tell it's big, but you can't be certain until you actually see it from a bird's eye view. The Milky Way consists of billions of distant stars that look like a string of lights from afar. So you just need to measure the distance between these stars and voila, you have the answer. Not really. I might have forgotten to mention opaque clouds of dust blocking your view. Some scientists were stubborn enough to run computer models of how galaxies form and evolve. There's a halo around our galaxy, so the scientists wanted to see if there was some sort of a dead end in the Milky Way. They found out that the Milky Way spreads for 100,000 light-years away from its center. It likely means that the entire galaxy is around 200,000 light-years across. The problem with this estimation is that halos don't tend to have some final border since they simply fade away. It's like pointing a flashlight and trying to see precisely where the light ends. In 2013, the Hubble Space Telescope captured an image of something 25 million light-years away. It turned out to be a spiral galaxy, later called ESO 3738, with at least 7 other galactic neighbors. And this galaxy is as thin as a pancake, a very shiny pancake. The telescope also took a photo of another galaxy cluster 65 million light-years away. It was called IC 335. It's another glorious glittering pancake floating in the vastness of space. The images the telescope took aren't the most accurate. It's hard to tell what exactly you're looking at. These disk galaxies have lots of dust clouds that can stretch for hundreds of light-years across. They're mainly located near the centers of galaxies and are invisible in regular light, but they can be detected with the help of a blue filter. Anyway, this IC 335 galaxy is an oval disk with huge clouds of gas and dust. This means stars constantly appear there. But not all galaxies create stars. A galaxy is born as a giant ball of slowly rotating gas that is steadily collapsing in on itself. As it starts spinning faster and faster, the pancake shape is formed. Ooh, pass me the syrup. It's like spinning pizza dough in the air after rolling it into a ball. The topping is stars, and the sauce is clouds of dust and gas. Are you getting hungry like me? Some galaxies can lose their gas and dust if they become part of a galaxy cluster. Then all these mini-galaxies orbit their common center of mass, with gas separating them. When a disk galaxy dashes through them like a speeding train, the pressure can blow away this dust and gas. From far away, it looks like you're staring at a DVD you're about to play. But if you traveled millions of light-years to get a closer look, you'd see a dim disk filled with stars. You wouldn't even be able to tell you're inside it. You'd also see a bright blob of dust left by the red giants in the middle of the galaxy. Red giants are massive and very bright stars with low surface temperatures. But the images of these galaxies don't actually show us their real color. Cameras make up some of these hues so that you don't have to look at something fuzzy or grainy. People don't actually know the real colors of distant galaxies. Our galaxy has a lot of gas inside, like me, so we don't need to expect our home to dry up anytime soon. In fact, the Milky Way still produces new stars, around 7 a year. But some galaxies fade out when they can no longer create stars. In the industry, they call it strangulation, and it happens when galaxies run out of gas, which means there's no more new material that can be used for star making. Gas and dust aren't the only things you can find in a galaxy. Just like a magician pulling a rabbit, flowers, or other things out of their magic hat, galaxies have other surprises, like planets, those balls of matter spinning around themselves and around other things. Well, technically, planets are far from being perfectly round in shape, but they aren't also flat like spiral galaxies. It's mostly because of gravity. Its force is so strong that a planet pulls everything towards its center, taking the shape of a sphere. In the process, all the edges and anything else that might stick out gets smoothed out. But the smaller a space body is, the less round it is. Take a comet. It doesn't always have a smooth surface. It's small, and therefore, its edges are rugged and pointy. Given the size of Earth, it's safe to say the gravity is strong here compared to that of the Moon or any smaller-sized space object. And because of our planet's constant rotation, there's an outward bulge on Earth. This tug-of-war between the gravity pulling inward and the planet's spin doesn't allow Earth to be a perfect ball. On top of Earth not being a perfect sphere, the planet is also tilted. This design flaw is responsible for the seasons we have. This tilt could happen because millions of years after Earth was formed, it probably collided with a protoplanet, a large space body developing into a planet. Venus is unique because it rotates backward compared to the rest of its peers. If you were standing on Venus, the hottest planet in our solar system, you'd see the sun rise in the west and set in the east. But you'd have to make it on time to observe this phenomenon. A day on Venus lasts for more than 240 Earth days. For a long time, scientists believed that the sun's strong pull on Venus was responsible for such a long day. But new theory claims that Venus used to spin just like Earth and the rest of the planets. But at one point, it just flipped its axis 180 degrees. It doesn't mean the planet abruptly stopped halfway through the rotation and started to move backward. When theory suggests that a large comet or object struck the planet in the past. This might have caused it to change the direction of its rotation, but many scientists doubt this theory. If you observe the moon for some time, you may notice that it's the same face staring at you every night. The truth is that the moon does rotate, but very slowly. It takes our planet's natural satellite 27 Earth days to rotate around its axis. Plus, the moon rotates at the same rate that it orbits Earth. The side we always see is called the near side of the moon, and the side that's not facing us is, you guessed it, the far side of the moon. It also has the nickname the dark side of the moon. Uranus's rotation axis is 98 degrees relative to the plane of the solar system, which basically means that the planet spins on its side. For a while, scientists believed that a large object firing through space knocked into Uranus, causing it to tilt. But here's one problem. Uranus's moons are covered in ice. A collision so powerful that it made the planet tilt would have resulted in disrupting the moon's movement and their position. But they seem relatively untouched, and all the ice covering them is still intact. But any major changes happening with Uranus would have generated enough energy to melt the ice. Another reason for Uranus's strange position might be its rings. Yup, Uranus has rings just like Saturn, except they're lighter and fainter. Saturn's rings are mostly billions of chunks of ice and rock floating in orbit. Some particles can be the size of a pebble, while others can reach the size of a house. Wow! Other particles are broken-up comets, asteroids, and moons torn apart by Saturn's gravity. If you observe the rings from afar, they look like colorful stripes made up of thousands of different streaks, but there are actually only 8 layers of rings. Uranus might have had rings that were just as glorious as Saturn's around 4.5 billion years ago. The balance between Saturn's gravity and its rings might be responsible for keeping the planet upright so that it doesn't tilt over. If Uranus had the same rings, they could prevent the planet from toppling over. The way to solve Uranus's tilting problem might be for the planet to get its rings back. They would help Uranus keep its balance. On the other hand, hey, we like it just the way it is.
There are a lot of unanswered questions in physics. How did universal energy and matter appear? Where did gravity come from? And much more. We've been trying for years to get answers to these questions, and one of the people who tried to do this was Paramahamsa Tiwari, the author of the so-called space vortex theory. What is this theory, and what does it say about the hidden laws of our universe? Let's figure it out. Paramahamsa Tiwari was the former executive director of the Nuclear Power Corporation, India. He took the space vortex theory, or SVT for short, first proposed by René Descartes and finalized it. He was always inspired by physics and its greats, even since his days as an electrical engineering student. After rigorous studies of the laws of physics, he discovered new equations defining matter and the mass and charge of the electron. After that, he came up with the SVT. This theory tried to explain the unexplained phenomena in physics, including the creation of the electron and gravitational, electrostatic, and electromagnetic energy fields, as well as other things. It also described the 6 hidden laws of the universe that underlie our entire world. But first of all, let's talk about the theory itself. Space vortex theory suggests that the universe is made up of vortices, or swirling patterns of energy. And according to SVT, these vortices are the fundamental building blocks of the universe. They're the driving force behind the laws of physics and the fundamental principles of our world. Basically, everything in the universe is connected and interconnected through these vortices. This theory isn't very based on any real observations, but rather on mathematical models and computational modeling. For example, some computational models showed how these vortices work in hydrodynamics and plasma physics. They showed that vortices in such systems can have a central point of attraction and can be interconnected. Other models were used to study how the energies inside the vortices move and how they can create different frequencies and vibrations. But some experts have criticized SVT for using only models and simulations. The biggest criticism is that this theory can't actually be tested. It relies on mathematics and not on some experimental data. That's why it's not accepted as a mainstream scientific theory. But it's still quite interesting and provides a unique perspective on the universe and our understanding of the laws of physics. For example, according to SVT, the universe has some underlying hidden rules that cause the creation of fundamental matter, their assembly, and movement. What are these laws and what do they say? Well, let's take a look at them. Law 1. The universe has only one primordial entity, space, i.e. absolute vacuum, that structures matter. This law states that space is the fundamental building block of the universe and that it's responsible for structuring matter. It suggests that space is the fundamental entity that creates and maintains the structure of matter, and that all matter in the universe is made up of the same fundamental particles, like electrons and positrons. Let's try to put it in simple words. Imagine that the universe is like a big Lego set. Just like how all the Lego bricks are made up of the same basic building blocks, the universe is made up of the same fundamental building blocks too. And these blocks are called electrons and positrons. But what holds these blocks together? Space, of course. Space gives it shape and structure, just like how the plastic container holds all the Lego bricks together in a set. So, the first law states that space is the fundamental building block that structures matter and holds everything together in the universe. Law 2. Matter is constituted with multiples of only one kind of fundamental particles, electrons and positrons. This law states that all matter in the universe is made up of the same fundamental particles, the electron and positron. These two are the Lego blocks we've talked about before. And, according to the second law, these tiny invisible particles make up everything, from a tiny atom to a giant galaxy. Just like no matter what the shape or size our Lego build is, it's still made up of the same building blocks. Law 3. The field distribution in space, as recognized by contemporary physics, linked with and emanating from matter, are effects arising from only one fundamental field in space. This law states that the fields recognized by contemporary physics, such as the electromagnetic and gravitational fields, are effects arising from a single fundamental field in space. It suggests that this fundamental field is responsible for creating everything that we observe in the universe. So let's try to put it simply. This time, imagine that the universe is like a big playground. All the different fields we observe, such as the gravitational and electromagnetic fields, are like different games we play in there. But no matter what we play, we're still in one fundamental space. This is the playground itself. It's the base that holds everything together. According to the third law, without the playground, we wouldn't be able to play any games. And without this fundamental field in space, we wouldn't be able to observe any fields in the universe. Law 4. There is no void in space anywhere in the whole universe except at the centers of the fundamental particles of matter, electrons and positrons. This law states that there's no truly empty space in the universe and that all space is filled with the fundamental field, the one we talked about before. It says that electrons and positrons can be found everywhere, and even the things we consider to be empty, like vacuum, are actually full of tiny particles. And according to this law, the only truly empty spaces we can find in the universe are at the centers of the fundamental particles, electrons and positrons. Law 5. From only one fundamental universal constant, all the constants considered universal in contemporary physics are derivable. This law states that all the constants considered universal in contemporary physics can be derived from a single fundamental universal constant. It suggests that all the constants in physics are interconnected and can be explained by a single fundamental principle. I know you've been doing a lot of imagining lately, but bear with me. This time, please imagine the universe as a big recipe. All the constants in physics, such as the speed of light, the gravitational constant, and the Planck constant, are like the ingredients. They're very different and there are tons of them. But just like how all the ingredients in a recipe are interconnected and come together to make one dish, all the constants in physics come together to make the universe. And just like how a recipe has a main ingredient that holds everything together, physics also has a single fundamental constant that holds everything together. Law 6. The spatial structure of submicrocosmic fundamental matter is repetitive uniformly in the spatial structures of macrocosmic bodies like planets, stars, and galaxies. This law states that the structure of the fundamental particles that make up matter is repetitive and uniform across all scales, from subatomic particles to macrocosmic bodies like planets, stars, and galaxies. It suggests that the same fundamental principles govern the structure of matter at all scales. Let's go back to the analogy with the recipes and cooking. Using different ingredients and combining them in different ways, the chef can create new dishes. These will all be different dishes and they can be very simple or very complex. But when creating them, the chef still applies the same basic rules and knowledge they have, right? And just like that, the universe also creates different structures, from atoms to planets, stars, and galaxies. But it still uses the same fundamental principles to create all these things. So, this law suggests that the structure of the fundamental particles that make up matter is repetitive and uniform across all scales. These are the 6 fundamental laws of the universe according to the SVT, and even though it's not accepted by mainstream science, it's still a pretty interesting concept.
You're traveling through deep space, circling stars and entire galaxies. Whoa, looks like this multicolored nebula will soon collapse under its own weight and explode like a supernova. Now let's carefully circle this black hole. Try not to get caught in its gravitational field, or it'll swallow you like a space monster. Wait. What's that strange structure right there? It's a glowing wall. And if you look closely, each glowing dot is an entire galaxy. That wall has about 100,000 of these galaxies. The Milky Way has 100 billion stars, so this wall holds a quadrillion, that's 10 followed by 15 zeros, of stars like our sun. This giant structure is called the South Pole Wall. It's located about 500 million light-years from Earth. By comparison, the closest star to our home is Proxima Centauri, and it's about 4.2 light-years away. Rockets can cover that distance in about 73,000 years. So the journey to the South Pole Wall may take longer than our solar system exists. And this wall is simply gigantic, even on a cosmic scale. It's about 1.37 billion light-years long. To give you an idea of how large that is, the Milky Way is only 100,000 light-years wide. But you can't see this wall even with the most powerful telescope. The problem is that the Milky Way itself obstructs your view. It's so bright that it's hiding this wall. It's like trying to look at the starry sky in a metropolis. The light pollution won't let you do that. Scientists have been able to detect this galactic wall by measuring redshift. We know that all objects in the universe are moving. They spread out from each other as a result of the Big Bang, which happened billions of years ago. And when galaxies move, their light waves change slightly. By measuring this change, we can understand what the object is and how it moves. And this wall isn't even the largest in our universe. This is the Hercules Corona Borealis Great Wall. It's a giant flat superstructure about 10 billion light-years wide. That's around 10% of the entire observable universe. And it's also a wall. That is, a cluster of galaxies. We were able to detect this giant structure by gamma-ray bursts. It's the brightest electromagnetic event in the universe. You could even see it in the far reaches of our universe. Such bursts are a very rare event. In the Milky Way, for example, it happens once every few million years. If we notice many such bursts in a short time from the same place, it means that there are many objects like the Milky Way in that place. So, there are a lot of galaxies out there. Another unusual giant structure in the universe is the huge, large quasar group. It's about 4 billion light-years across. So it takes a photon of light almost as long as our planet has existed just to get from one side of the structure to the other. And if you put the huge, large quasar group on the scale, it would be 6.1 billion times heavier than our sun. Scientists have found that there are at least 73 quasars in that structure. These are some of the most unusual objects in the universe. They are the active cores of galaxies. At the center of a quasar is a supermassive black hole. This giant eats up the matter around it. A wild force of gravity twists the matter around the black hole, forming a disk. And this disk is the source of the strongest radiation out there. By comparison, the radiation from a single quasar is tens or hundreds of times stronger than that of all the stars in our galaxy put together. Because of such strong radiation, we can detect quasars, even at very long distances. That's why they're also called beacons of the universe. Scientists use quasars to study the universe and the movement within it. One of the most distant quasars from us is about 13.1 billion light-years away. This makes it one of the oldest objects in the universe. It appeared about 690 million years after the Big Bang, and it's almost 3 times older than our solar system. It's still glowing with extreme brightness, about 4 and 14 zeros times brighter than the sun. Scientists explain that at the center of the giant is a supermassive black hole, 800 million times heavier than the sun. All these giant structures are just building blocks of our universe. Look, this is our solar system. Now, zoom out a little, and this is where our home star is in the Milky Way galaxy. Zoom out again. Here's a local group of galaxies. All the bright spots here are galaxies. Here's Andromeda, and here's the Triangulum galaxy, plus a few dozen other slightly smaller galaxies. They're all gravitationally connected. The size of this structure is about 10 million light-years. That's 100 times the width of our galaxy. Zoom out, please. This one is the Virgo supercluster. It's 20 times larger than the local group. There are about 30,000 different galaxies, and the mass of the whole thing is about 1 in 15 zeros solar masses. Zoom out again. Laniakea. This structure is almost 3 times larger. It includes the Virgo supercluster and other smaller clusters. And there are about 100,000 galaxies here. It's not over yet. Zoom out one more time. Here's the Pisces-Cetus supercluster complex. This giant galactic structure contains about 60 clusters of galaxies. So there are more galaxies in it than grains of sand in the desert. You know what to do. Zoom out! Phew, this is the observable universe. There are over 500 billion galaxies. And the stars? Well, there are about 1 billion trillion stars. The observable universe has its own structure. Clusters of galaxies form chains and walls, as you've seen before. But these strands are separated by huge regions of absolute emptiness. These areas are called voids. In these places, there is no matter at all. There are fewer molecules in the voids than in an empty room. One of these voids has a very mystical reputation. It's the Eridanus supervoid, or the cold spot. It appeared here only 380,000 years after the Big Bang. It's almost 1 billion light-years wide and could hold hundreds or thousands of galaxies with trillions of stars. Some scientists believe that this cold spot may have been the result of the largest collision ever, a collision of universes. There's a theory that our universe is some kind of bubble, a huge sphere that contains all these walls and chains of galaxies. Now imagine that there's an infinite number of these bubbles. They could be parallel worlds or different universes. Many years ago, one bubble came close to the bubble of our universe. Their walls touched, and the two universes connected for a while. It's like two drops of water coming together. But that universe kept moving. The area where the bubbles joined became thinner and thinner until that connection broke, and the two bubbles detached from each other. At this point, the second universe ripped some of the material out of our bubble. All those galaxies that used to fill the Eridanus supervoid ended up in a parallel universe. Scientists supposed we might travel through other bubbles. Flying to the supposed wall of our universe would take forever, and then it would take even longer to fly through interuniversal space. So we have to use portals, or wormholes. Here's how it works. Imagine a piece of paper with point A on one side and point B on the other. Instead of moving all the way across the sheet of paper, we just fold the sheet so that point A is right above point B. All that's left to do is make a small hole, and the journey takes only moments. Some scientists believe that such shortcuts through universes lie inside black holes. But how do you survive falling into a black hole? You just have to pick one that's big enough. It's all about gravity. Imagine you're falling into a black hole right now. The closer you get to it, the stronger effect it has on you. It intensifies with every inch. At one point, the gravitational force that affects your head is much stronger than the one that affects your feet. Then you turn into spaghetti. Yum. But if you choose a supermassive black hole, like the ones at the centers of galaxies, the gravitational force in them increases gradually. They can be millions of times heavier than the sun and much bigger, but the gravitational force on your head and your feet will be almost equal, and you will still feel comfortable. Who knows? Maybe if you manage to survive a fall into such a massive black hole, you'd find yourself in a completely different universe where different laws of physics apply. But so far, this is just a theory.
During the recent years, scientists made 2 breakthrough discoveries about our universe. Thanks to new technologies, we've looked into the distant past. And we've learned something that can change our understanding of the universe forever. What are these discoveries and what do they mean to us? Let's find out. Recently, we unveiled the first color image from the James Webb Space Telescope. It's a mind-bending photo capturing thousands of ancient galaxies. This oldest documented light in the history of the universe dates back over 13 billion years. That's just 600 million years after the Big Bang. It's like getting a sneak peek into the universe's baby album. But that was just the beginning. Astronomers were expecting to see some tiny young galaxies. But what they found was a real surprise. Impossibly early, impossibly massive, and all that from just a tiny red dot. The lead author of the study, Ivo Laba, was working at the computer as usual, and suddenly he got 2 numbers. Age, 13 billion years. Weight, 100 billion stars. When he realized what that meant, he nearly spit out his coffee. But that red dot was just the beginning. The next day they found 5 more galaxies just like this. Turns out, these 6 massive galaxies are as old as the Milky Way itself. The entire research team was in disbelief. They were like, "Wait, what? These guys couldn't be that mature so early in time. Did we make a mistake?" But nope. The James Webb Space Telescope, the new cool guy on the space block, just has some serious skills. It can see through dust clouds with its infrared vision and spot galaxies that were previously invisible. Move over, Hubble. There's a new stargazer in town. But why is it shaking things up so much? Because this discovery affects our understanding of how galaxies formed. Let's try to explain. A long time ago, 13.8 billion years ago to be precise, our universe was born. It was chilling out for a while, and then it started to form the first galaxies. And these galaxies were full of gas and dust. Eventually, this gas started turning into stars. Some galaxies were more massive and had more stars, and some were lighter and had almost no stars at all. In any case, they all grew gradually. The stars in them were born slowly and smoothly. That's how our current models explain this. But these new observations from the James Webb Space Telescope show an unexpected surprise. Looks like, even in the early universe, our ancient friends had lots of stars. More than what we would ever expect. If that's the case, then these galaxies are like the overachievers of the universe. They skipped the small and gradual growth phase and went straight to being giant universe breakers. According to our current cosmological model, they shouldn't even exist. But they do, so it looks like after the Big Bang, the stars were forming much faster than we thought. Which is pretty weird. This could mean that there's something missing in our understanding of the galaxy formation. As you can see, these universe breakers are really living up to their name, causing a potential total consensus among scientists. The universe was like, "Hey, I'm about to flip cosmology models upside down." But let's not jump to conclusions. There are many theories that could explain these mind-boggling discoveries without breaking the standard model. For example, maybe the light we're seeing isn't coming from stars at all, but from the swirling disks of doom around supermassive black holes. These colossal cosmic beasts can gobble up matter and spit out a dazzling light show. And James Webb Telescope's keen eye is picking up on these enigmatic accretion disks like never before. Or maybe these galaxies could be playing hide-and-seek with us. Maybe there's more to the story that we haven't seen yet. After all, the universe is vast and mysterious, and we've only just begun to scratch the surface. And whoa, we really need to slow down here. Before we even try to explain all this stuff, we need to confirm whether these ancient galaxies really are that old. Although even if they're actually just supermassive black holes, it still shows an astounding change. We'll have to wait about a year to find out. One thing's for sure, the James Webb Space Telescope has definitely taught us a valuable lesson. Expect the unexpected. And this is just the beginning of unexpected. Ivo Laba's team wasn't the only one who made such a huge breakthrough. There's also a team that claims that they've unlocked the secrets of the universe's past, and that's worth 2 Nobel Prizes. Move over, James Webb Space Telescope, because this discovery came from an antenna that's smaller than a fridge and costs less than $5 million. Talk about space bargain hunting! The astronomers caught this signal that showed some surprises. It was coming from the earliest stars of our universe, back in the days when they were just beginning to twinkle. Say hi to our celestial ancestors again. Now, the signal was pretty weird. The temperatures were unusually low, and there was a pronounced wave that left astronomers scratching their heads. What could be causing all this? Well, there's a theory. Dark matter may have been at work, and if that's the case, then we can really be on the verge of a great discovery. Imagine you're looking at the night sky filled with stars, but there's something else there that you can't see. It's like an invisible cloak that covers the entire universe. Scientists call this mysterious stuff dark matter. Dark matter is like the ghost of our world. It doesn't emit, absorb, or reflect any light. We can't see it with telescopes or our eyes. That's why we call it dark matter. But if we can't detect it in any way, how do we know it exists? Because of its gravitational pull. One day we noticed that our understanding of how galaxies were created was incorrect. According to our calculations, they should have been some chaotic gas, but something held them together, turning them into spirals, like some kind of invisible glue. Then we thought, maybe this invisible glue really exists. If the moon was invisible, we would still suspect that it exists somewhere because its gravity affects the tides on Earth. This is also the case with dark matter. Its gravity influences the motion of galaxies and other cosmic objects. In fact, dark matter makes up a huge chunk of the universe, about 27% of it. Moreover, the normal matter we can see, like stars, planets, and galaxies, only make up about 5% of the universe. So even though we can't see dark matter, there's actually more of it in the universe than everything we can see. Scientists are still trying to figure out if dark matter exists and what it can be made of. Some theories suggest that it could be made up of exotic particles that are different from the particles that we're used to. Others think that it might be some kind of weird, undiscovered form of matter that doesn't interact with light at all. Anyway, it's an intriguing mystery, and if we ever confirm the existence of dark matter, our understanding of our world will change forever. So now you can understand why the excitement in the scientific community is palpable. If this discovery is confirmed, then we will get the first real proof of dark matter. This discovery may be even more important than the Big Bang itself because, as astronomers put it, we are made of star stuff, and so we are glimpsing at our origin. But of course, we still have to wait and explore all this in great detail. In science, one should never rush to conclusions. And while scientists study this stuff, we'll be here, on the edge of our seats waiting for the next space blockbuster to unfold. The universe never ceases to amaze us with its wonders. Who knew that such a small and humble antenna could unlock such cosmic secrets? It just goes to show that in the vastness of space, even the tiniest discoveries can have the biggest impact. Keep looking up, and who knows what other cosmic surprises are waiting to be uncovered.
Look at these two pictures. At first glance, one might think, well, aren't they showing the exact same thing? Truth is, they don't. But both these subjects are some of the most complex structures humans have ever had the chance to study. The first image shows a cluster of galaxies from our universe. The second is just a small neuron in the human brain. After seeing these images, some were quick to compare them. Is the universe nothing more than a huge brain? Now let's not get too excited. Before we go into describing all the similarities between the universe and the human brain, there is something we need to be aware of. It's a little thing called apophenia. And it's when our brains make up similarities between two objects that are seriously unrelated. The best example is when we look at clouds and start to see all sorts of cute animals and weirdly shaped objects. We might be doing the same thing when looking at those two initial pictures. Maybe it's just our brain making up similarities where there aren't any. Some scientists became fascinated with this huge brain universe idea. They wanted to make sure it was not just a weird coincidence. There had to be a way they could measure how the universe compares to the mushy organ inside our heads. So they started with the brain. It's probably one of the most complicated things we know in the whole universe. That's because it's packed with more than 80 billion neurons. These cells are responsible for taking information from our senses and sending out messages all over our body. Try to think of neurons as workers in a factory. They don't just do their work, they actually communicate with each other, thanks to these elements called axons and dendrites. The axons are responsible for carrying electrical signals away from the neuron's body to other neurons or muscles. Dendrites, on the other hand, have the task of receiving that information. All of them together make this mega network of about 100 trillion connections. The universe is one big social network itself too, but this time it's made up of galaxies. You might picture the universe as stars and planets with a ton of empty space between them. It's not quite right. What we can see and measure is known as the observable universe, and it's really vast. Think about 90 billion light-years across, containing hundreds of billions to maybe a few trillion of galaxies. These galaxies, like the one we're standing in at this very moment, are bundled together in groups. Our Milky Way is friends, in a way, with galaxies like Andromeda and Triangulum, and altogether, they're a family called the Local Group. This family of galaxies is part of an even bigger bunch called the Virgo Supercluster. From what we can tell, the space between them might not be empty. It's filled with these threads made up of regular matter, but there might also be this mysterious dark matter doing its thing. Scientists didn't stop there. They decided to take it a bit further. They started by examining thin slices of the human cortex, the part responsible for our thoughts, memories, and even our consciousness. The next step was to compare them with equally thin slices of the universe from a computer simulation. Now it's obvious there's this enormous size difference between the brain and the universe. But the way they looked at it kind of made them somewhat comparable. As they zoomed in, think 40 times magnification, these scientists began noticing that the structures were very much alike. At this zoom, the brain's neural network looked like the universe's galaxy clusters. To make sure they weren't just imagining things, they used two clever methods. The first one looked at how these networks connected and how densely packed they were. They noticed that the middle part of a neuron, or its nucleus, is way tinier compared to its connecting fragments. Likewise, galaxy clusters are tiny when you look at the super long connecting threads between them. The second method was about checking how organized these networks were versus just being random. They looked at how everything was structured around each connection point, whether it was a neuron in the brain or a galaxy cluster in the universe. The resemblance doesn't stop there. We know that our brain is mostly water, about 70% to be precise. Now the cosmic web in space, it too has about 70% of something, only this time it's dark energy. Water and dark energy may not be the most important elements in each of their structures, but they might still play a part in how everything sets up. The analogy continues. You see, the space we'd need on a computer to map out the universe is almost the same as our brain's memory storage. Somewhere in the ballpark of 2.5 petabytes. So theoretically, a chunk of the universe could fit in our brains. Or flip that, and our entire life's memories could get stored in the universe's network. There are differences too, and we have to be aware of them to make sure we're assessing things properly. For starters, the universe is pretty much the same all over. It doesn't change its composition that much, regardless of where you travel in the observable area. But our brain, not so much. Different parts have different jobs. Also, our brain connections send information depending on things like what you're seeing or touching. On the flip side, the universe's links are just energy. There's also a difference between how these two structures came to be. It turns out that the patterns we see when we're gazing up at the stars are all shaped by gravity and some weird unseen force called dark matter. Massive fireworks in space called supernovae can also affect this cosmic wallpaper. On the opposite side of the spectrum, our brains got their shape from evolution. That long process where animals, including us, get to pass on the best features and data they've learned to their offspring. So, if a trait like a certain shape of the brain helped our ancestors dodge a hungry tiger, that trait got passed down. Our brains are also built the way they are because they're supposed to act like a superhighway for our thoughts. Quick thinking was crucial for people back in the day when they needed shelter from wild animals or the elements. Now, especially if you're a fan of sci-fi literature, you might be wondering, if the universe is like this immense brain, what might its body look like? We might as well be living in someone else's head. We like to think of humans as evolved, intelligent, and at times, hard to understand creatures. But what if we're just tiny neurons in a larger, more complex structure? Well, for the time being, we can only let our imaginations run wild. There's no way we can test at this point what's outside our universe. By all means, we don't even know how large it is. By looking at the parts we can see, the estimations are that the universe is about 95 billion light-years in diameter. Even if we'd somehow manage to travel at the speed of light, though that seems a bit impossible at the moment too, it would take an enormous amount of time to reach those supposed edges of the universe. There's also the theory of the multiverse. We don't have much tangible proof of this idea either, but it does claim we live in a universe out of many. Ours has time and space. Other worlds may have different rules and components. Life may look differently out there in ways we can't even understand. Having a better understanding of the universe is just as important as figuring out our brains. You see, we still have many unsolved mysteries right here under our noses, or behind our noses to be more precise. There are a lot of things we've yet to figure out about the human brain, like how we store and retrieve memories. We know that each time we learn some new piece of information, our brain changes. But we don't have the entire process mapped out, and it looks like it might take a while before we fully understand it.